right, so good afternoon, everyone. I welcome you back to this wonderful session. Presenting before you this wonderful tutorial is the mentor Hamper Kliman. So, today we shall be looking at sound waves, and of course, this was supposed to be our Telegram lesson, but it shall be recorded, and I'm going to make sure that I add in all the ingredients that are going to make this particular topic simple. So without even wasting much time, we are simply talking about sound waves. So if I may ask a question, what exactly is a sound wave? What exactly is a sound wave? Or let me just say, what is a wave? Okay, what is a wave? So a wave by definition is just a disturbance, okay? A disturbance which is traveling through a medium eliciting energy. Okay? It is a disturbance traveling through a medium eliciting energy. Okay? That is just one thing that you must understand about um, about waves. Okay? So of course we know that a wave is just a disturbance. It is a disturbance traveling through a medium. As it is traveling through a medium, it is exerting energy. Okay? As it is traveling through a medium, it is exerting some energy. This concept is very important for us to understand. So there are two types of waves. We've got sound waves. So we've got longitudinal waves. Okay, we've got longitudinal waves. We've got longitudinal waves. And then we've got what we call transverse waves. But when we talk about a sound wave, we are simply talking about a longitudinal wave. Okay? Now, if we talk about longitudinal waves, if we talk about these longitudinal waves, we are simply talking about, okay, we are simply talking about waves whose particles travel to, okay, to and fro along the direction of the medium. Okay, we are simply talking about particles that are traveling to and fro along the direction of the wave. So the particles are traveling to and fro along the direction of the wave. That is a longitudinal wave. In transverse wave, they are at perpendicular to the direction of the wave. So now, a very good example of a longitudinal wave is a sound wave. It's a sound wave. And that is exactly what we shall be looking at today. Now, in order to understand sound waves, In order for us to understand sound waves, we use the concept of a tuning fork. Okay, so we are going to use the concept of a tuning fork. Okay, we are going to use the concept of a tuning fork. Yes. Now, how do we use the concept of a tuning fork? If this is our tuning fork, if for example we say that this is our tuning fork and this tuning fork is not yet in motion, we can use this as our scenario A. But if we apply a certain force on this tuning fork, there is going to be a point where it will start vibrating to and fro. That is, it will go to this direction, and at the same time it will come to this direction, even this side. It will go in this direction, at the same time it will come back in this direction. So you expect that there is going to be a point where this tuning fork is going to be with this particular motion. Yes. Okay, that is possible in physics, and we know what is happening. So we're going to have a time when we're going to have this turning fork in this particular direction. Okay, we can name this as our B. And at the same time, there is going to be a point where it will go, okay, outward. That is the to and fro that we're talking about. So there's also going to be a point where it's going to be spaced in this direction. This guy will be going in this direction. Okay, you have this particular movement. Okay, it is vibrating. So of course this is going to be C. Now notice what is happening here. This guy and this guy are close to each other. So you expect that the particles are going to contain a low molecular density. So they are going to contain a low molecular density at this point. When these particles are separate from each other, you expect that they will contain a high molecular density. Now, if we were to plot this particular kind of motion, if we were to plot these waves, we are going to have something like, because in B, these particles are containing, they are of low molecular density, you expect that these waves, when we draw these waves, they are going to present in this manner. Okay, they will be so separate from each other. Okay, like this. But with this guy here, notice that the distance has been enlarged. So this implies that there is the force that is working on C is very high, and these particles are going to contain a very high molecular density. So you expect them that they are going to be close. Okay, they'll be so close to each other, like that. But with time, you expect, because they are vibrating in air, there is that air resistance that is occurring. So they will lose so much energy with time, and you expect again that there's going to be this motion. Okay, there's going to be this presentation. So this part here, where the waves are so separate from each other, is what we are calling as a rarefaction. This point here, where the waves are close to each other, is what we are calling as a compression. So at what point is the sound going to be produced at a very high frequency? You expect that it is at a point where we have a successful compression. It is very important for you to understand that particular concept. This is what we shall be using. I'll be using the formula of the tuning fork to come up this concept of a tuning fork, to explain to you how we are going to come up with several formulas. Of course, let's try to look at the characteristic. Okay, characteristic of sound wave. Okay, so from the characteristic of a sound wave, from the definition, particles are traveling back and forth along the direction of the medium. Okay, so one characteristic is that, which is a prominent characteristic, is that particles are traveling back and forth along the direction of the medium or of the wave. Yes, this is a prominent characteristic of sound waves. Okay, you have these particles that are traveling back and forth along the direction of the medium. I explained, you have this guy moving in this direction. At the same time, at some point, it will be moving back in this direction. So it is back and forth in the direction of the medium or in the direction of the wave. Okay, that is a prominent characteristic of a sound wave. Okay, now these sound waves can be categorized into three. Okay, so we can say categories of sound waves. So these sound waves can be categorized into three. The first one that we are going to have is called an audible wave. So the first one we are going to have is called the audible wave. The second wave which we are going to have is called the infrasonic wave. These are very important MCQ, so please take note of them. So we have the infrasonic. Okay, infrasonic. We have the infrasonic wave. And the third one we are going to have is called the ultrasonic wave. Now, what do we mean by audible wave? The audible wave is that wave which is carrying the frequency of sound that is audible to man, which you are able to get. That frequency which you are able to get, which you are able to hear, normally is called the audible frequency. Okay, so it should be in the range sensitivity to that which you are able to hear. Okay, so audible wave is a wave which is carrying a frequency of 20,000 Hz. Yes, we know this. Or it can also be written as 20 kilohertz. Okay, but basically just convert it to hertz. Okay, just convert it to hertz. Yes. Okay, that is very important. Infrasonic wave. Infra meaning below. So this is going to be a wave which is carrying a frequency that is going to be below the audible wave. So this frequency is going to be below 20,000 Hz, or it must be below 20 kilohertz. Okay, then for ultrasonic wave, we are simply talking about a wave which is going to be above the audible frequency. So it's going to be above 20,000 Hz, or it will be above 20 kilohertz. That is very important for us to understand. Coming to the application, in case they ask you the application, when exactly do you use these waves? Okay, so of course, what is important is the ultrasonic wave, because it goes beyond 20 kilohertz. So of course we can use it to produce images of small objects. Okay, can be used to produce images of small objects. Which wave is this? The ultrasonic wave. The ultrasonic wave. Yes. What is the second application? Okay, it can also be used as a diagnostic tool. We can use it as a diagnostic tool, not really better than the X-ray, but this guy is able to see beyond the X-rays, able to see clearly organs such as the liver, the spleen, damages, injuries that are there. So it can be used as a diagnostic tool and can be used for certain treatments. Okay, so we can use it as a diagnostic tool and used for certain treatments. What else? Okay, it can also be used to measure the flow of blood in the body by Doppler effect. Okay, can be used to measure blood flow by Doppler effect. By Doppler effect. That is very important to understand from the application. Okay, now we can go deep into our sessions. Suppose you have, okay, you have this tuning fork. Let's say you have this tuning fork, okay. Well, let me just write the heading. Let's now talk about the speed of sound in air. The speed of sound in air. Okay, so we have the speed of sound in air. Now, if you have this tuning fork, and you have this tuning fork vibrating, okay, in this direction, you have this wave in this direction, you have a wave going back again, then you have this wave in this direction, you have a wave going back again. You expect that this wave is exerting a certain force. It's exerting a certain force where this force is being exerted into air, okay, into air. So as this force is being exerted into air, there is a certain, it is exerting what we, a wave which we are calling as a sound wave. A sound wave. This sound wave is going to be traveling because of energy that is being elicited from this particular guy. So now whenever a sound is moving in air, we are interested to find its velocity. So which formula exactly do you apply? For you to find the speed of sound in air, you use the formula V is equal to, then, okay, so this one, okay, so this one is the speed of sound in air. So of course, we are going to use this one, this formula. The velocity, okay, the velocity is going to equal to, okay, 331 meters per second multiplying T over 273 kelvins. Now, this V is simply the velocity measured in meters per second. This 331 meters per second is the prominent speed of sound in air at 0 degrees temperature. Okay, then T is simply the prominent given temperature in kelvins. Prominent given temperature in kelvins. They will give you OS. Then of course this is a constant, which is 273. 273 is equivalent to 0 degrees, so we just put it in kelvins. So it is very important for you to understand this formula. We shall be using it oftenly. Okay, we shall be using this particular formula oftenly. How about if we have this sound which is moving in fluids? The speed of sound in fluid. How do you calculate the speed of sound in fluid? In a medium that contains water. Okay, so for you to measure the speed of sound in a medium, okay, which contains fluid or water, you are going to consider, look, if this is a cup and this is cup B, this is cup A, cup B, these particles are not close to each other. Then here the particles are close to each other like this, in this manner. Okay, they are close to each other. The speed in A is going to be a little bit, okay, low compared to B. Why? Because B has got a very high compressibility of particles. Okay, compressibility of particles. The particles are too compressed. Because of that, sound is going to travel at a very high medium, at a very high speed. Now, this compressibility is what we are calling as the bulky modulus. The compressibility is what we are calling as the bulky modulus. Henceforth, the speed of sound in a fluid is going to be given by the formula square root of the bulky modulus over the density. Okay, the density. Of course, the V is the speed measured in meters per second. This is B, which is the bulky modulus, which can be measured in pascals, but usually it will be, remember, it's pascals, so of course they can put it in pascals or in newtons per meter squared. Okay, then of course this is the density, which is measured in kg meter squared. It's very important for us to understand this. So in case you have not been given the bulky modulus can be found by using the formula pressure over the change in volume multiplied by okay, so this is going to be change in volume. Okay, change in volume with multiplied by the prominent volume, okay, which is multiplied by the constant volume. Okay, so bulky modulus, this formula can also be written as pressure multiplied by the constant volume over this change. So it's going to be V final minus this one is volume initial. So bulky modulus must always be positive, don't make it negative. So pressure multiplied by the constant volume, this is constant volume, then over volume final minus volume initial. But mostly they'll give you the bulky modulus and the density. Use this particular formula. Your units should be meters per second. It is very important for us to understand that concept. Okay, how about if we have this sound which is moving through a solid medium, let's say a rod. Okay, so we say the speed of sound, in solids. Solids like what? Rods. How do you calculate the speed of sound in solids? So whenever you have been given a question, what they're saying, calculate the speed of sound traveling through, let's say, a rod, okay, a spring, as long as it is a solid medium, okay? This time around, your velocity is going to consider a certain constant, which we are simply calling as the Young modulus over the density, okay? So this is Young modulus, so the V is just the velocity measured in meters per second, okay? Then we have the Young, this is called Young modulus. Usually they will give you because it's a constant, okay? Young modulus, this is the density, okay? Usually they will also give you this density. You just have to calculate the velocity, okay? The velocity, of course, should be in medians, in meters per second. That is very much important for you to understand, okay? That is very important for you to understand. Now, for the speed of sound in air, you need to understand that it depends on the temperature, this T. So usually they will give you the temperature, okay? And if they give you the temperature in degrees Celsius, convert those degrees Celsius into kelvins, okay? That is very important for you to understand. We now come to energy and intensity of a sound wave. Let's talk about this important factor, okay? Let's talk about this important factor. Energy and intensity of a sound wave. So it's very important that you pay extra attention on this particular part. Energy and intensity of a sound wave. Now, let me go back to a tuning fork. So let's say we have this guy here. This guy is our tuning fork, okay? Yes? So, this tuning fork, if it begins to vibrate, you expect it moving in this direction. At the same time, there is going to be a point when it's going to move in this particular direction, okay? And I demonstrated at first from these diagrams. At the same time, at the time that it moves in this direction, you expect that it's going to also move in this direction. At the time that it moves in this direction, you expect that it's going to also move in this direction, okay? Now, for it to create a certain sound wave, it is eliciting a certain force. I explained a certain force where in thin air it is exerting a certain force in thin air, okay? Now there is air resistance which is occurring, and that is what is going to cause the vibration of the tuning fork to die, okay? But as this tuning fork is exerting a certain force on thin air, you expect that it is eliciting a certain energy which is enabling the movement of these particular particles, okay? So what is being exerted here what is being exerted is called energy. Okay, is called energy. Now, the rate at which uh, uh, um, uh, these waves are going to be elicited is going to depend on the surface area of this turning fork, right? The surface area. So you're also going to consider a certain area, okay? At a given what? At a given time. Okay, that is very important for you to understand. Now, if that is the case, then this means that if we were to calculate the intensity, then our intensity is going to equal to the energy which is enabling the movement of these particles, okay, the energy which is enabling the movement of these particles over the change in time, okay, multiplied by the inverse of area, okay, which is just 1 over A. A is for the area, okay, A is for the area. Now, if this is the case, this formula is very applicable, okay, it's very applicable, especially if you have been given the energy, the time, and the area. You can use this concept. Now, we know that this particular part, okay, this particular part where you have the energy over the change in time, because this is just the energy exerted, okay, this is just the rate at which energy is flowing, the rate at which energy is flowing. So the rate at which energy is flowing is called power, okay, the energy at which rate the rate at which energy is flowing is called power. So from this formula, where there is this part, we can replace with P, so that because that is called power. So we can say, therefore, we have P. So we are going to have this formula. So we have P multiplied by 1 over area. So hence our intensity is going to be power over area. Okay. So this power is measured in watts. Then this area is going to be measured in meters squared. Because of that, our intensity is going to be measured in watts per meter squared. Okay, so this formula you should also take note. It's very important for us. All right, that is very important for us to understand. Now, okay, now remember that the faintest sound, okay, the faintest sound that a human ear can get is 20,000 hertz. The intensity at this sound, okay, the intensity at this sound is equal to 1.0 multiplied by 10 to the power negative 12 watt per meter squared, right? That is very important for us to understand. That is the intensity at which we are able to get this particular sound. Yes? Okay, that is clear. Okay? Now, this 1.0 multiplied by 10 to the power negative 12 is what we're calling as the threshold. It is called the threshold of hearing. It is called the threshold of hearing. Henceforth, if we are to calculate the intensity, if we are to calculate of course, from the decibels, of which I haven't just started decibels, but we can calculate intensity from there. Remember, I just want you, let me just use this formula. Okay, for now, decibel is equal to 10 log intensity over the intensity initial. Okay? Now, if we are to get this part here, where we say our intensity 2, because this is intensity 2, the initial is the one which is down there, where we say our intensity 2 is over intensity 1, okay, then this is going to be equal to power over area over power over area. Yes, this is the formula that we have here. Okay. Now, we know that the area, if we're using this, the area for a round figure or a sphere, is going to be 4 pi r squared. So this can also be written as intensity 2, that is intensity 1. So this is going to be intensity 1, okay? Then this is going to be intensity 2 over intensity 1 is going to equal to P over 4 pi r squared, okay? This is r squared 2 over P over 4 pi r squared 1. Then if this is the case, then this is just the same as intensity 2 over intensity 1 is going to multiply P over, this is 4 multiplied, so 4 pi r squared 2 is multiplying, okay? Then this guy is going to be on top, so it will be 4 pi r squared 1 over P. So this guy and this guy can go, this guy and that guy can go. Therefore, our intensity 2 over intensity 1 is going to equal to r squared 1 over r squared 2. This formula, take note of this formula. It's very important. When do you use this formula? You use this formula if you have been given one intensity, at least you are given at least one intensity, okay, one intensity, then you are also given both distance. One intensity, both distance. Distance, I mean r squared 1, r squared 2. Yes, we can calculate any of the intensities, either this one, given the r2, r1. Yes, or we can calculate the distance as long as they want you to calculate the distance given the intensity. If you want to calculate the distance given the intensity, this is the formula to use. Okay, use it to calculate distance or intensity given the set values. Or just say set values. They can give you either of the two, but please, this is the formula to use. How do you remember it? All the ones must be correlating. All the twos must be correlating. So we are using the X concept. We'll do more practice questions on this particular on these things, so that you understand how to just go about them. Okay, that is very important for us to understand. Now let's go to intensity in Debye cells. Intensity in Debye cells. The relative intensity of a sound wave is called the Debye cell level. The relative intensity of a sound is called the Debye cell level. Okay? This statement is very important. It will help us. The relative intensity of a sound wave is called the decibel level. Now, which formula do we use if we want to calculate intensity? Okay, remember it's supposed to be in decibels. These are the units. So the formula which we use is B, because this is the decibel level, is going to equal to 10 log of intensity over initial intensity. And of course, B is our decibel level and it is measured in decibels. Okay, so this formula is very important. Now we know that the initial intensity is equivalent to 1.0 multiplied by 10 to the power negative 12 watt over meters per second over meters squared. So this formula can also be written as B is equal to 10 log the intensity over intensity initial. So we can also use this to calculate the intensity. If we want to calculate the intensity, how do we change the formulas? How do we transform the formulas? So of course we have B is equal to 10 log over intensity over intensity initial. So to make this intensity the subject, the first thing that we need to do is to divide by 10 this side, also divide by 10 this side, so that this guy and this guy can cancel. So we are going to have B over 10 equal to log intensity over intensity initial. Yes, but here remember that there is a power 10. This is a power 10, so this guy can be taken to this side. Then it's going to be 10 to the power B over 10. And that is going to equal to the intensity over the intensity initial. So this can, and that can cross multiply. So if we cross multiply, then we are going to have our intensity equaling intensity initial is going to multiply 10 to the power B over 10. Take note of this formula. You can also use it to calculate the intensity. Okay, you can use it to calculate the intensity. Okay, given the decibel level, the decibels. If you have been given the distance you want to calculate intensity, just go to this guy here. Okay, if you have been given, if you want to calculate the intensity given the power, okay, the power, okay, that is where now you come to these formulas which I gave you here. Okay, so this is very important for us to understand. Okay, it's very important for us to understand. Okay, now how about, let's say, if you have been given a decibel level. Okay, let's say you have been given, okay, the first decibel level, and then you have been given a certain distance which they are calling as R1, and it is measured in meters. And then they also give you another distance which they are calling as R2, also being measured in meters. Then they say, can you calculate the decibel, which you are going to call as your decibel level 2. How do you go about this? There is a formula which I just want you to know. okay, which is just the second debit cell level is going to equal to the first debit cell level which you are given plus, instead of putting 10 log, it will be 20 log R1 over R2, where these are the distances which you will be given in the question, okay, in the question. So, having understood all these particular concepts, it is very important that you practice as many questions as you can, and you are able to solve intensity, you are able to solve the speed of sound in air, the speed of sound in water, in fluids, in solids, all those formulas. Okay? All these formulas, they are going to help you calculate all these things. Okay? So coming back to our summary, if you want to calculate the speed, if you want to calculate the speed of sound in fluids, the formula is V is equal to the square root, the bulk modulus over the density. Okay? If you want to calculate the speed of sound in fluids, you use this particular first formula. The speed of sound in air, it will always be 331 meters per second multiplied by the temperature over 273 kelvins. This is in air, so this one is in fluids. This one is in air. How about in solids? The speed of sound in solid is going to be the square root of the Young modulus over the density. This one is for solids. Okay, if you want to calculate the intensity, if you want to calculate the intensity given the power and the area, intensity, let's say given the energy and the time, okay, and the area, then intensity is going to equal to energy over change in time multiplied by the area. Okay, but remember, we changed this formula I showed you. This can also be calculated if, for example, you have been given the power, you can use power over area. Okay, and this should be, this should be in watts per meter squared. What is the other formula for calculating intensity? The other formula for calculating intensity, okay, we say that intensity is going to equal to the initial intensity multiplied by 10 power B over 10. How about if you are given distances, what formula do you use? The formula we use is intensity 2 over intensity 1, and we said that it is the x concept, so we're going to have R2, that is going to be R1, so we're going to have R1 squared over R2 squared. Okay, then this is how you calculate this, the intensity. These are the most prominent formulas for calculating intensity. Okay, then of course, if you want to calculate the debit cells, we use this formula. Okay, it is going to be 10 log intensity over intensity initial. Okay, then of course, if you want to calculate the depth cell level 2 given the distances, depth cell level 2 is going to equal to depth cell level 1 plus 20 log, given the distance, we say R1 over R2. So we'll be using these formulas most frequently. If you found this video helpful, consider subscribing or sharing to others so that we can be of help to one another. The next time we come, I'm going to teach you how to manage questions under Doppler effect. Okay, so we're going to be doing the Doppler effect. Please consider following this series on sound waves. I'm making everything easy for you. Thank you so much.